Alright, let's consider a beam. Fixed at point A. And simply supported at point B. With a concentrated load of 10 kilonewtons at the center of the beam. So let's say this is 3 meters, this is also 3 meters. And let's put also the UDL and this distributed load with a triangular shape. So let's say this is a uniform UDL from point A until the middle of the beam, and now we have this triangular distributed load from the middle of the beam until point B. So let's say this UDL is 10 kilonewtons per meter. And this triangular goes from 10 kilonewtons per meter to 0 at point B. So the question is, draw, so basically, okay, so the question is the bending moment and shear force diagrams for this beam. Alright, so I'm going to draw the beam here again. So basically I'm going to do the free body diagram. So we have the beam, something like this. I'm going to represent UDL here, and then this triangular, distributed load, and I'm going to represent here the concentrated load of 10 kilonewtons. So this is 10 kilonewtons per meter. We need to include now a coordinate system. So let's say this is my x direction, this is my y direction. We need to include, or we need to replace the supports with the reactions. So at point A, we have a point A fixed, so we have a horizontal reaction that I will call AX, and we have a vertical reaction that I will call AY. These two reactions, they constrain the movement in the horizontal and in the vertical direction. The rotation about point A is possible, so it means there is no moment as reaction. Now at point B, we have a simple support, so we have only a vertical reaction that I will say is By. Okay, so this is a free body diagram. So basically we have the beam, we removed the supports, we replaced the supports with the reactions, we have all the external loading, and we have a coordinate system. So this is my free body diagram. What we are going to do now is we are going to use the equilibrium equations so that we can calculate the reactions first. So the equilibrium equations are summation of forces in the x direction needs to be equal to 0. summation of forces in the y direction needs to be equal to 0. And we have summation of moments about any point. I'm going to choose point A, needs to be equal to 0. So this is a two-dimensional problem. We have only 3 equilibrium equations. Before we start writing the equilibrium equations, I'm going to replace the distributed loads with an equivalent force at the centroid of each distributed load. So I'm going to start with this uniform distributed load here. I'm going to replace this UDL with an equivalent force located at the centroid of this rectangle of this UDL. So I'm going to say that I will have this force here, equivalent force replacing this UDL. This force is located, so this distance from here to here is 1.5 meters. Half of 3 is where the centroid is, and this equivalent force is equal to the area of this rectangle, to the area of this rectangle here, which means this is going to be equal to 10 kilonewtons per meter times 3 meters. We are going to do the same. We are going to do the same for the distributed load, for this triangular distributed load here. I'm going to replace this with an equivalent force located at the centroid of this triangle. So basically I'm going to replace this distributed load with this force, and this distance from here to here is going to be 2/3 of 3 meters. Okay, and this equivalent force is equal to the area of the triangle, so it's going to be equal to 10 times 3/2. Alright, so we have everything. Again, I'll write the equilibrium equations. So basically I will have, for the first equilibrium equation, summation of forces in the x direction equal to 0. We will have ax equal to 0. So we don't have any more forces in the horizontal direction, so it means this reaction is going to be equal to 0. Summation of forces in the y direction equal to 0. We have the reaction at point A plus the reaction at point B minus the 10 kilonewtons, this one, this concentrated load, minus 10 kilonewtons. We have now the equivalent forces, this one, for the UDL on the left, so minus 30. And we have now the equivalent force for the triangular distributed load, this one. So this is minus 15. Minus because they have opposite direction from the y-axis. So this is all we have in the vertical direction. So this needs to be equal to 0 to be in equilibrium. And now for the moments about point A, so the two reactions at point A don't produce any moment. I'm going to start with the moment produced by the reaction at point B. So this moment is equal to this force times this distance, which is 6 meters. So 6 times the force By is anticlockwise, means is a positive moment. I'm going now to do the moment produced by this concentrated force of 10 kilonewtons about point A, so I need to multiply this force by this distance, which is 3 meters. And that moment will be clockwise, so is minus, is negative, 3 times 10. I'm going to do now the moment produced by this UDL. So basically I'm going to use the equivalent force and multiply this equivalent force by this 1.5 meters. And then I will have the moment. That moment will be clockwise, so is minus as well. So minus 1.5 is the distance times the force, which is 30 kilonewtons. And the last moment we need to add is the moment produced by the triangular distributed load, by this equivalent force. And then I need to multiply this by this distance here, which is 3 meters plus 1/3 of 3 meters. So basically it is 4 meters. Okay, so minus 4 meters times the force, which is 15 kilonewtons. So this is all the moments we have about point A, so they need to be equal to 0 to be in equilibrium. And from these equations, as you can see, we can use this equation to solve for the reaction By. Then after having the reaction By, we replace in this equation here, and then we can calculate the reaction Ay. Okay, so if we do that, we should obtain By equal, so I'm going to do the maths here. I obtain By equal to 22.5 kilonewtons, and after replacing this on the second equation, we get, for Ay we get Ay equal to 32.5 kilonewtons. Okay, so let's continue our analysis now. So we can now say that our beam will have this reaction 32.5 at point A, we'll have 22.5 at point B, the distributed loads, so something like this, 10 kilonewtons per meter. The concentrated load here, 10 kilonewtons. So this is our beam. So what we are going to do now is we are going to cut the beam in these two different sections. So basically we are going to do something like this. We are going to cut the beam in this section, and then we are going to cut the beam in this section here. And then we are going to separate the beam in two parts. We are going to use the part on the right side, so basically when we cut here, we will have this reaction of 22.5 at point B. We have this little bit of this distributed load, and so we did cut the beam in this section, right? So, and then we need to include the bending moment. I will call this bending moment mx, function of x. And we need also to include the transverse shear force, this one that I will call I will call this my transverse shear force P as a function of x. And of course, we need to consider a local variable x, that I'm going to say that my local variable x is going to start at point B and pointing to the left direction. So basically x equal to 0 means point B. There is one more thing we need to do, is we need to get the height of this triangle. So we need to get this height here, and this height here is given by this equation 10 over 3 times local variable x. This can be easily seen if we replace x by 3 meters. We should have the height equal to 10, which is correct. For x equal to 0, we should get height 0. So everything works fine. Right, so of course that this analysis is valid. This is valid. For x bigger than 0 and lower equal to 3. If x is bigger than 3, it means we are cutting the beam in section A and between A and the midpoint of the beam, so we need to have a new free body diagram for that. We are going to do that later. So this analysis is for x between 0 and 3. Don't forget, x is starting at point B and going into the left direction. So what we have to do now is we have to, for the transverse shear forces, we have to do the summation of forces in the y direction, saying that it is equal to 0. So in this case we have the transverse shear force Bx, we have the reaction, and then we have now the distributed load, the triangular distributed load. So the equivalent force is the area of the triangle, and the area of the triangle is going to be given by 10 over 3 times x. So this is the height. I need to multiply the height by the width of the triangle, which is x. So this becomes x squared. And I need to divide this by 2. So I'm going to say something like this. 2 times 3 in the denominator. Okay, so that's all we have for the summation of forces in the y direction. So this needs to be equal to 0. So from this equation we get the transverse shear force Bx is going to be equal to 10 over 6 x squared minus 22.5. Okay, we are going to do now the bending moment equation. So we are going to use the equilibrium equation for the moments. So we are going to do summation of moments about the section where we did cut the beam. So I'm going to say summation of moments about section X needs to be equal to 0. So what do we have? So in the section where we did cut the beam, we have the bending moment mx is a clockwise, so minus mx, clockwise moment, so that's why you have a minus. The transverse shear force V doesn't produce any moment about that point. It passes through that point. We have the moment produced by the reaction at point B, so that moment will be anti-clockwise, so positive. The length is x, and the load is 22.5, so that moment is going to be 22.5 times the length, which is x. And then we have the moment produced by the distributed load, the triangular distributed load. So what we have to do is we have to consider an equivalent force that is acting on the centroid of the triangle. So I'm going to represent it here. This equivalent force acting in the centroid, and this distance here from here to here, this distance is 1/3 of x, is the location of the centroid of the triangle. And then we can now say, of course, this equivalent load is the area of the triangle, and as we said before, that area is 10x over 3 is the height. We need to multiply this by the width, which is x, so this becomes x squared, and we need to divide by 2. This is the equivalent load. And now with the load and with the distance to section X, we can obtain the moment. That moment will be clockwise, so minus. And then we have the load, which is 10 over 6 x squared. And we need to multiply the load by the distance, which is 1/3 of x. And then we get the moment produced by the triangular distributed load about the section X where we did cut our beam. So these are all the moments we have, so this needs to be equal to 0 to be in equilibrium. And so from this equation we get the bending moment mx equal to 22.5x minus 10 over 18 x power 3. Okay, so we have to do now the analysis for section between A and the midpoint of the beam. So I'm going to use a new page. So I'm going to draw here again the beam. The reactions, so this one is 22.5 kilonewtons. This one is 32.5 kilonewtons. We have the distributed loads, 10 kilonewton per meter, and we have the concentrated load here, 10 kilonewton. So what we are going to do now is we are going to cut the beam in this section now and look at the right side again, like we did before. So what we are going to have is we are going to have this right section of the beam. Now we need to represent all the forces we have on this right section, which is 22.5 kilonewtons reaction at point B. We have this 10 kilonewtons concentrated load. We have this triangular distributed load, and we have this small bit of our UDL. And we, of course, we did cut the beam in this section, and this is my local variable x, starting again at point B and going all the way until the section where we did cut the beam. And again, we need to represent the transverse shear force, Vx, and the bending moment, Mx. And then again, we use the equilibrium equations. So let's start with summation of forces in the y direction equal to 0. So we have the transverse shear force, Vx. We have the reaction at point B, plus 22.5. We have the concentrated load, now, which is minus 10 kilonewtons. We didn't have this in the previous, when we did cut the beam previously, in the previous page, but we have now, when we cut the beam between point A and the midpoint of the beam, and when we look at the right side, we need to consider now the concentrated load at the midpoint of the beam. The only thing we need to consider now are the distributed loads, so we need to replace, for the triangular distributed load, we need to replace this UDL, this triangular distributed load with an equivalent force located at the centroid of the triangle. This equivalent force the magnitude of this equivalent load is equal to the area of the triangle, so basically it is equal to 10 kilonewtons per meter times 3 meters over 2. And the location of this load is in the centroid, so the distance from here to here is 1/3 of 3 meters, so this is equal to 1 meter. So we can include now the triangular distributed load in our equilibrium equation for the forces. So it will be a negative minus, and the equivalent force is equal to the area of the triangle, so it is 30 over 2 is 15 kilonewtons. We need also to include now the UDL, so we need to include this UDL here, this rectangle here. We need to replace this rectangle by an equivalent force located at the centroid of this rectangle. So that's what I'm going to do now. I'm going to replace this rectangular distributed load with this equivalent force, and this equivalent force is equal to the area of the rectangle, so it is 10 kilonewtons per meter times x minus 3 meters. So x minus 3 meters is the distance from here to here. This is x minus 3. X is the total length from point B to section X, and then we need to take off 3 meters for the section from point B to the midpoint of the beam. Okay, so now we need to include that in our equilibrium equation, so it will be minus 10x minus 3, which is the area of the rectangle, and that's all we have. So in order for this to be in equilibrium, this needs to be equal to 0, and from this equation we can get the transverse shear force as being equal to 2.5 plus 10x minus 3. Now for the bending moment, we need to use the equilibrium equation for the moments about section X equal to 0. So we have the bending moment minus mx. Transverse shear force doesn't produce any moment. We can include the moment produced by the reaction at point B. It's going to be plus 22.5 x. X is the total distance from point B to section X. We need to include now the concentrated load. It's going to be a clockwise moment, so minus. The distance for the moment is x minus 3 times the load, which is 10 kilonewtons. We need to include the triangular distributed load, so the moment produced by the equivalent force is going to be clockwise, so minus. The distance is going to be this total distance here. I'm going to represent it in red color now. So we need this total distance from here to here, so that we can calculate the bending moment produced by the triangular distributed load. And this distance is x minus 3. So x minus 3 is this, plus 1 meter. So this makes the total distance x minus 2. And then we just need now to multiply this by the force, equivalent force, which is 10 times 3 over 2 is this one, right? So 10 times 3 over 2 is 15. So we just need to multiply this by 15. Then we have the moment produced by the triangular UDL. And now we need last one we need to include is the moment produced by the rectangular distributed load, this one. Okay, so for that we need this distance from here to here, and this distance is x minus 3 over 2. Okay, so the moment will be also negative, is clockwise. I need the distance x minus 3 over 2, and then I need to multiply this distance by the force, which is 10 times x minus 3. And this is all I have, so this needs to be equal to 0 to be in equilibrium. And from this equation we obtain mx is going to be equal to 22.5x minus, so let's say we have 10x here, it's minus 25x, and then we have here 30 plus 30, so plus 60, and we have at last we have minus x minus 3 squared times 10 over 2. So we can simplify this a little bit more. We can say mx is going to be equal to minus 5x minus 3 squared. Oh, I think I don't have space. So I'm going to continue here, so we can say mx is going to be equal to minus 5x minus 3 squared minus 2.5x plus 60. So this is bending moment equation, this is the transverse shear force. For the first section, this is the transverse shear force. This is the bending moment equation. Okay, so now that we have the equations for the bending moment and shear force, we can start drawing the diagrams. So I'm going to draw the beam again here. These reactions are 32.5 and 22.5. Okay. So now I'm going to extend these lines, something like this, into two sections, and we are going to plot here the transverse shear force, and we are going to plot here the bending moment. Of course, don't forget that our x starts at point B, so it comes from point B to the left. Okay, so let's start with this section. Let's start in this section here for x between 0 and 3. I'm just going to copy the equations. This is for the shear force, and now for the bending moment we have okay, so these are the equations we are going to use. So starting with the transverse shear force, so we have for x equal to 0, the transverse shear force is going to be minus 22.5. So let's say this is minus 22.5. And then for x equal to 3, we have the transverse shear force equal to, let me just do the calculations here. Minus 7.5. So it means, so let's say this point here is minus 7.5. So it means that we have a quadratic distribution for shear force, so we will have something like this. For shear force in this section. For the bending moment, when x is equal to 0, we have bending moment 0, so this point here. And when x is equal to 3, we have, just a moment, sorry. We have 52.5, and then we have something like this because it's a, so let's say this is 52.5. We have a cubic distribution. We'll have something like this, right? This is our bending moment equation for section for x between 0 and 3. We have now to do the other section for x between 3 and 6. I'm going to delete these equations now, and I'm going to consider now the equations for the other section, which is for the transverse shear force. (2.5) x minus 3, and for the bending moment mx we have minus 5 square minus 2.5x plus 60. Okay, so let's see, when we have x equal to 3, this term is 0, so we have 2.5 times 3 plus 60. We have 52.5, so the same point, this point here. And when we have x equal to 6, x equal to 6 means we are at point A, support. So if I replace x by 6 in the bending moment equation, we get bending moment equal to 0, as expected, because at point A the bending moment should be 0. We don't have any moment at point A. So we can then plot the bending moment, something like this, and for the shear force, when we replace x by 3, we will get the shear force of 2.5. So let's say this is 2.5. And when we replace x by 6, we have a shear force of 32.5. So, and is linear. This equation for the transverse shear force is a linear equation of a line. So I can just say this is 32.5, and then we have the linear distribution for the transverse shear force. It is very interesting, as you can see, that for example, if you look at the transverse shear force at point B, at this point we have a transverse shear force of 22.5, which is exactly the same as the reaction at point B, and at point A we have a transverse shear force of 32.5, which is also exactly the same as the reaction at point A, as expected. We can say the same thing for the bending moment. The bending moment at point B is 0, because we don't have any moment at point B. The bending moment at point A is also 0, because we don't have any moment at support A.